Hello, guys. Welcome to the session, and I hope all of you guys are doing good. So let's get started with today's session. So today we are going to proceed further with what we started in the last class about the linear regression. And today what are we going to do is we are going to understand if you want to apply the linear regression model in your data set. If you remember in the last class, we have seen that suppose I want to predict how many marks I am going to store, I am going to score uh, based on the hours I studied, right? So I can predict that. So now we will be doing the same here. So basically when I want to predict a real value number, in that case, we are using the regression. All those things we have discussed in the last class. So now we have to come up with the understanding of what are assumptions which we have, right? We'll talk about the assumptions which we have. So this is what we discussed, that data should be linear in nature, and I have to create a line which is passing from the majority of the points. So now there are certain assumptions which should be there. And if those assumptions are very much meeting, in that case, I can say that I can very well apply the linear regression. If those assumptions are not meeting, in that case, I can say that linear regression is not, we can apply. So let's start with the understanding here. The first assumption which we have is the relationship between your x and y should be linear in nature and not a curve, right? That means if I have my x and I have my y, then it should be linear in nature. That we have discussed quite a bit. Linear means it should have a good correlation. Linear can be positive as well. Linear can be negative as well, right? I am okay with both, but it should be linear in nature. But if we are having some curve type of data, for example, this is my data set. In this, I cannot create a linear regression model, because what linear regression model is, it is creating a line which is passing from the majority of the points. And here it's not happening like that because the data is very much curved, right? Here I will be applying some other type of algorithms, but linear regression will not work here. So that is the first assumption which we have, that the relationship should be a line, not a curve. Linear relationship is an assumption. Imagine plotting hours studied versus test scores. If the dots are roughly form a straight line, we are good. If they form a curve or a zigzag, then linear regression may not work well. Good scenario when it's a line shaped relationship. Bad when it's wavy, curved, or random patterns, right? So that is the first assumption which we have, that my relation should be linear in nature. You can see here also, right? It's a simple diagram where our studied and test score, and I see that there is a linearity and we are good. So in this particular data set, I can very well apply the linear regression. Second assumption which we have is prediction mistakes should not influence each other. Independence of errors. Say 10 people take a test. The model makes small prediction errors called residuals for each person. These errors should not be connected. One person's prediction mistake should not affect another's prediction. Random dots in a residual plot, good. Wavy or zigzag pattern is bad. Let's try to understand this with an example. Suppose my data is like this. and this is my model line, right? Now let me create one more chart, which is basically talking about the errors, right? For my data points, this is, let's say, experience, and this is my salary, and here I am plotting the errors. Basically your what do you say, this is my error, y-axis is my error, right? Y-axis is my error and x-axis is my actual experience, right? Here I'll show you the plot directly, something like this, right? This is my plot. Hour studies is my x, how many hours I studied, and y is my errors. Error is what? Actual value minus the predicted value. Basically we are predicting something, right? So this is my data set. This blue line is the prediction line. My actual value is this. This is my actual salary. And this is my predicted salary. The difference which I have is the error. Same way here also. Actual salary, predicted salary. This is my error. Okay. This error is also known as residual. Now think of a scenario. I am showing you two data set. Right? One data is like this. Normal linear data. And this is my model. The blue line. What are my errors? The difference between the actual and the predicted is my error. Actual minus predicted is my error. Actual minus predicted is my error for all the dots. Right? Now let me create the plot for errors. This is my hour studied. This is my marks scored. This is my error. Can I say here that majority of my errors are around zeros, all of you? This is bit lesser than zero. This is more higher than zero. Bit lesser than zero. Bit lesser than zero. Bit more than zero. Bit lesser than zero. Lesser than zero. More than zero. Almost zero. Bit more than zero. Lesser than zero. Can I say that? Actual minus predicted value. This error is almost zero or around zero. Can I say? If you guys are not understanding, you can ask me. I will repeat that. But you should tell me if you're not understanding it. Okay. I'll repeat. No problem. But I need response from everyone on the all the class, 14 learners. Okay. So here my error is almost zero. So if I am creating this line, let's say this is my zero line, right? This is my zero line. Can I say that my points or my errors will be around zero, right? Some thoda sa dur, right? It's something like this. And that is what you can see in this plot as well. Your errors are well scattered around zero. This is my zero line. Okay. That is one scenario. This is a good chart. This is a good chart. What is a bad chart? Let's see this. Let me create another example. My data is like this. First of all, can I apply linear regression here? What do you think? No, because it's not linear in nature. But let's say we applied, right? Let's say we applied. We applied the linear regression. We got something like this line. Okay. Now, can I say for this particular point, my error is higher? For this particular point, my error is higher. 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 For these points, my error is almost zero, right? Now let's create the plot for the error. For the first point, let's say this is my zero line. This is my zero line. For the first point, the error is more towards the negative side. Second point, closer. Third point, positive. Fourth point, higher. Fifth point, more higher. Sixth point, lower, 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 lower. Again, it is increasing, 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 increasing. Error is increasing, error is increasing, decreasing, 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 decreasing. Can I say I am seeing one pattern in the error as well? Right? Error was more. So more, less. So less, like that. So I see a pattern out here as well, right? And this is not good. Your error should be scattered in nature around zeros. If you go back, independence of errors. Can I say that in this particular picture, this error is dependent on this error? Because it is increasing, then decreasing, then increasing, then decreasing. That means my current value is dependent on the next value, or next value is dependent on the current value. I can say that. Something like a time series data. For example, let's say share market, share price. Right? My share price is increasing, then decreasing, then increasing, then decreasing, then increasing, then decreasing. Right? Some patterns like this. So that is what the pattern I can see here also. Okay. So that is not good. For the regression point of view, that pattern I don't want. Prediction mistakes should not influence each other. Looks like it is influencing, right? My current value is smaller. I know next value will be higher. It will further higher. Here the error is very high. I know that next error will be lesser. So it is lesser, and so on and so forth. So there is a relationship, and that relationship we don't want. So when you are having a random dots, we are good. But when we are having a wavy or zigzag patterns, we are not good. Okay. So that is the second assumption. For that, we normally create this type of plots to check how the errors are scattered. If the error is very much scattered on the zero, we are happy, right? Model is good. Okay. Third one, scatter of error should be even everywhere. Wait a minute. I think the title, yeah, that's fine. So assumption is homoscedasticity. Same spread of residuals, the spread variance of the errors should be uniform. It shouldn't look like a cone or fanning out of squeezing in as values increase. All prediction mistakes have a similar size. If mistakes get higher or smaller depending on the input, there is a problem. Technical term, if the scatter isn't even, it is called heteroscedasticity. Lot of texts out here. I'll explain that in a very simple term. This is my data set. And one more data is present here. Okay. Now, I want to create a line which is passing from the majority of the points. Let's say this is my experience. This is my salary. Can I say this guy is an outlier, a very rare in number? All the guys are having higher experience, their salary is getting higher. But for this particular guy, the experience is high, but his salary is not that much high, right? So this guy is an outlier, rare in number. Now, suppose I want to create a line. Can I say that this line is actually wrong? My line will be something like this. Because of this outlier, my line will tilt as well, right? Because it will consider this point also. And if it will consider this point as well, my line will be tilted towards outlier. And because of that, can I say that my error is increasing? For this is my actual record, this is my error, which is okay. But for this guy, if blue line I will be considering, I will be happy with a good prediction. But which line I am considering? I am considering the red line. My error automatically increased, right? Here my error automatically increased. Here my error is okayish. Here my error is increased. If I would be going with the blue line, I would not have that much error. But it is coming in because of this outlier. This red line is the finalized line because of this outlier. Till this point, is it making sense, all of you? So can I say that outlier should not be there in my data set, right? I don't want outliers in my data set. That is one scenario. I'll give you second scenario. This is my data set. In this particular data set, what do you see? You see that your data is expanding here, right? Your data is expanding. V shape, it's becoming V shape. And think about your error line, how the error line will look like. Your error line will look like this. This is my zero error. Initially, your errors are less. Initially, your errors are less, but slowly your errors will increase, right? Because of these points, my error will increase. My error is increasing. So automatically, my error plot is also becoming like V shape. What I was expecting, all should be around zeros. But because of this V shape, my error is also becoming V shape, residual plot. And that is also what I don't want. So basically, when your points are in a fan shape or a V shape, or there is an outlier, that leads to wrong predictions, right? Because here you can see we have a lot of wrong predictions, right? The error is very high. Error is very high. This problem is known as heteroscedasticity. There should not be any heteroscedasticity in your data set. Or I can say in a layman, there should not be any outliers in your data set. Your data should be homoscedastic. It should not be heteroscedastic. Or as a layman, there should not be any outliers. Is that making sense, all of you, this assumption? Okay. Now, next one is prediction error should follow a bell curve. Very interesting. For this, I will be going back to my uh, this plot, right? In this particular plot, can I say that majority of my errors are around zero and bit of scatterness, which I was expecting? So if I create a bell curve, what is a bell curve? Bell curve is something like this, normal distribution. Now, what I am saying is that majority of my errors are around 0. Majority of my errors are around 0. So majority of my errors are around 0. Right? And there are some errors which are bit scattered as well. There are some errors which are scattered as well. What is this? What is this? This is nothing but my bell curve. Right? So basically, when you have this type of scatterness, majority of the values are around 0. Few are bit of a far from the 0. So here you can see that majority of the errors are around 0 and few are outside 0. And that leads to a normal distribution. And that is what it is saying, that my error should follow the normal distribution. Normal distribution of residuals, that is error. The error should look like a bell curve. If you plot them, this is important for doing accurate statistical tests. Right? Here you can see that the left chart, majority of my errors are around 0 only. Right? Majority of the errors are around 0 only. And then there are few errors outside. So it's, if I try to create a curve, it's something like a bell curve. Right? Is this plot making sense? Why I am saying my error should be in a bell curve, all of you. Second is this plot, which is known as QQ plot. It's not an outlier. Why it is an outlier? This data set. This is my line. So these points are outliers. So here the error which you have, can I say the error is more than 0? Yes, right? It's more than 0. Around 0, bit more than 0. So that is what I am saying here. These are what? If you go back to the histogram, what is the error? It's around 0 only, right? 0 to 4, 0 to 4. If it is very far, then it is outlier. If my error is 0 and my error coming somewhere here. So now this guy is an outlier. Getting it? If you're around 0, I'm okay with that. My curve should be something like a normal distribution. If my curve is coming out to be something like this, or if my curve is coming out to be something like this, then here are the outlier present. Then that's a problem. Is that making sense, all of you? What Pranav asked and what I responded. Okay. All right. So that is done. Let's talk about this QQ plot. How many marks I got? That is my actual Y. And what predicted value I got? That is the predicted marks. Okay. Now, if let's say my actual marks is 10 marks and my prediction is also 10. The point is here. If my actual marks is 20, prediction is also 20. My 20 is here. If my actual marks is 30 and prediction is also 30, my 30 is here. So can I say that when your actual marks and prediction marks are exactly the same, I will be getting a 45-degree line, all of you? Right? So if your data is around 45-degree line, we are happy. Some curve will be there. Some error will be bit higher, some error will be bit lower. That is possible. But if your line is around 45-degree, we are good, right? These are some of the farther points. That's okay. If there is an outlier, then this guy will be very high. ये नीचे होगा, right? This will be very low. This will be very high. अगर कुछ ऐसा curve आता है, when the curve is like this, then there is a problem. Because here you have a higher errors. Here we have a higher errors. It's like S. But when you are having this smaller s or thinner s, I'm okay with that. Because you are around 45-degree line only. Because my actual values and my predicted values are on the same lines. Is this making sense, all of you? Perfect. So that was one more assumption. And when we are creating the models, we create all these charts and we check whether things are fine or not. Okay. Next one. There should not be any multicollinearity. Or I can say there should be low or no multicollinearity. Now, what does that mean? If you are using multiple inputs, as of now, we only discussed that I want to predict the marks based on the hours I studied. But let's say I want to predict the marks based on the hours studied plus how many hours I am sleeping plus how many hours I am playing the game, right? So in that case, I am having more x's. Hour studied is 1x, hours sleeping is 1x, and hours playing is 1x. And what is my y? Y is my how many marks I got. Okay. So when we are having the multiple inputs, let's take an example here. Let's say I want to predict the salary based on the experience. Okay. My experience is increasing, my salary is increasing. Second, when my age is increasing, my salary is also increasing. Right? But what is the problem? The problem is when my age is increasing, my experience is also increasing. This feature is my x2. This feature is my x1. And here x2 is correlated with x1 or not. Right? Correlation we discussed. So it is a positive correlation. So can I say that x2 is correlated with x1? And if that is happening, that is a problem. That is what multicollinearity means. No or low multicollinearity I want. If you are using multiple inputs, hours studied, practice tests taken, sleep hours, they should not be too similar. Here, age and experience is too similar. That's why you are getting this 45-degree line, right? That's why you're getting this type of correlation. If two inputs are super related, very high correlation, the model gets confused, like trying to separate salt from salty water. If two features are having a good correlation, then that is bad for my model. If two features are having no correlation, that is good for my model. Right? Now, why model gets confused? Let's try to understand this. And these are the ways to check the correlation. We already aware of this, right? So we have this correlation matrix and I can see that our studied is highly correlated, right? Like that. So this correlation matrix, we have these correlation numbers. We are already aware of that. We already discussed that how these calculation happens. But why model get confused? Let's try to understand that. Suppose my data is like this, experience and salary. I have this data set where the correlation is there. I have another data set, like in the same data set, I have another feature, age and salary. When my age is increasing, my salary is also increasing. Now, can I say that if I take experience and age to predict my salary, I am generating one equation called y is equal to m1 into experience plus m2 into age plus c, right? Linear equation. Let's say m1 is 2. Let's assume m1 is 2. And let's assume m2 is 3. So my equation is what? Y, that is nothing but salary, is equal to 2 into experience plus 3 into age plus C. So what is the coefficient of experience, all of you? What is the coefficient of experience? 2. What is the coefficient of age? 3. Now, let's keep it aside for now. Let me come to this part. Can I say that my experience is also having a relationship with the age? Right? Now, can I say that if I create one equation, age is equal to M1 into experience plus C, it will make sense? Because there is a linearity. This equation will make sense. I will get a nice equation because there is a linear combination. Let's say my age is coming out to be 3 into experience plus C. So can I say that my age is nothing but 3 experience, all of you? Right? Now, if I put this guy here, can I say that my equation coefficient will change? Experience was 2 experience, age is 3 age, and what is age? 1 age is 3 experience. So 3 age is how much? 9 experience. And 9 plus 2 is what? 11 experience. So can I say that now my equation will change to 11 and 0, all of you? Because I have age, which is 3 experience. 3 experience is 1 age. 3 age is how much? 9 experience. 9 experience plus 2 experience is 11 experience. So 11, 0. So can I say that my coefficients are not stable because of this relationship? Right? And if my coefficients are not stable, my model is also not stable. Okay? And that is the reason we don't prefer to have the multicollinearity. When we are having multicollinearity, your model will become unstable. I have written somewhere here. Confused, right? So that is the relation, that is the correlation, multicollinearity, and we normally don't want that. If we have it, like in our example, we had that. For creating my equation to predict the salary, I will be only choosing one feature and I will discard the another feature. Right? I will discard the another feature. Are you guys clear with this multicollinearity, all of you? How to check it? These are the charts which can help you to check, right? So these are my x's, for example. Test score is my y. These are my x's, right? So this is my y. So these are my x's. And the same x's you can see here as well. So you can see that with the practice test completed and hours studied, the correlation is highest. The correlation is highest. That means this feature, hours studied and practice test completed, are highly correlated. So in that case, I will be choosing only one feature for creating my model to predict the test score. Either I will choose hours studied or I will choose practice test completed. Right? I will not go with both. Okay. And same way you can see in the plot as well. This hour studied 45-degree line. Highly correlation. Okay. So that is the idea. If there is a correlation of around 70 plus, 0.7 plus, we have to consider removing one of the features. It's again industry standard. This can be changed as per the client requirement as well. Okay. But if you see correlation of 0.7 and above between two independent variables, then we can consider removing one of the variables. Okay, that is the idea. There is one more way of calculating your multicollinearity, which is known as VIF. We will discuss that later on once we'll learn machine learning, okay, in detail. As of now, I'm not putting that. Next one is there should not be any pattern over time. There should not be any autocorrelation. What is autocorrelation? As a layman, zigzag. Can I apply linear regression here? Good. Is linear regression is good here? What do you think? No, right? We discussed that multiple times. Here, I cannot apply linear regression. So that is what it is saying. This mostly applies when the data is collected over time. The prediction error should not be formed a trend. If yesterday's error is influencing today's, that's autocorrelation and it messes up the model. Random noise is good. Zigzag or trending error is bad. Right? That we already discussed earlier as well. So when we are having something like a zigzag type of pattern, that is known as autocorrelation because your current value is dependent on the previous value. And that we don't want. Okay. That is the last assumption which we have. So these are the important assumptions which we have. One is linear relationship. Second is independence of errors. Third is homoscedasticity. Fourth is normal distribution of errors. Fifth is no multicollinearity. And sixth is no autocorrelation. If these six values or if these six assumptions are very much satisfied, we are very good to go with linear regression. If the assumptions are not satisfied, in that case, we have to think of some other model. Okay. Here you can see the picture also, all the different types of assumptions which we have. Now we will be understanding about how we can calculate the equation of we discussed y equal to mx plus c and all, but how this calculation happens, right? We'll try to understand that. And also we'll try to understand these variations, right? We'll discuss about that in some time. So let me proceed further. All these things I'll discuss later on. Let's proceed further directly to this page. Okay, let's discuss this now. I want to predict. Predict means what? I am creating a machine learning model, which we discussed in the last class as well. What machine learning model is. I am coming up with one equation. Equation is my machine learning model, right? This is my equation, which I want to come up with. How many marks I will be getting based on the study hours. M1 is my coefficient of study hours. C is my intercept. Let's try to understand it with a picture. This is my data set where I have the study hours and I have the marks. This is my data points, right? So now when I am creating a line, here x is equal to 0 at this point. At x is equal to 0, what is the value of y? At x is equal to 0, this is my x. X is equal to 0. That means this entire term will become 0. What is the value of y? Value of y is c. So basically c is nothing but this value, also known as y-intercept. At what point your y is getting cut by the line? That is known as y-intercept. That is the value of c. Right? That is my c value, y-intercept. Second is this m1. What is m1? m1 is nothing but slope of a line. m1 is nothing but what is the slope of a line? Right? What is the slope of a line? m1 is nothing but slope of a line. You can also say it as, let me zoom this, right? So it's something like this. This is my, let's say, point x2, y2. and this point is my x1, y1. So what is this guy? x2, x1. So what is this? x2 minus x1. Same way, what is this guy? y2, y1. What is this? y2 minus y1. So can I say that this is my y2 minus y1 and this is my x2 minus x1? So how much my y is changing when my x is changing? That means y2 minus y1 upon x2 minus x1. How much my y is changing as and when my x is changing? That is nothing but height upon base. And this angle, let's say, is theta. So what is height upon base? As per the trigonometry, height upon base is nothing but tan theta. Right. So basically, what is my slope? This is my line. What is the slope? I have one point here. I have one point here. This is what I am dropping. Let's say this is my x and y. So I am dropping this point. This is my x2. I am dropping this point. This is my x1. I am dropping this point. This is my y1. I am dropping this point. That is my y2. So this guy is my x2 minus x1. This guy is my y2 minus y1. So height upon base. Height is y2 minus y1. Base is x2 minus x1. Height upon base is nothing but tan theta. And that is nothing but my slope. Rate of change of y with respect to x. That is the slope of a line. Is that making sense, all of you? How much my y is changing with the respect of x? No. There is one property of a line. The property of a line is that your line will always pass from the average, right? There is one property of a line. Your line will always pass from the average. So let me modify this formula. The formula is m is equal to y2 minus y1 upon x2 minus x1. And what I mentioned, that line will always pass from the average. So what if I can write in place of y2, yi, and in place of y1, y average upon xi minus x average. Right? I am making my 2 as I because I can be anything, 1, 2, 3, 4, whatever. So I, and line is also passing from average. So average is also one of the points on line. Average is also one of the points on line. This is my line. Average is one of the points as well. So in place of taking x1, I am taking x average. In place of taking y average, y1, I am taking y average. So basically, this is my line equation, yi minus y average upon xi minus x average. I can very well write this equation as this. Is this making sense till this point? मेरा लाइन हमेशा एवरेज से पास होगा और एवरेज से पास होगा तो मैं यहाँ पे y एवरेज लिख सकता हूँ और एक पॉइंट को मैंने yi दे दिया. Same way I gave xi also one point. Okay. Now I will modify this equation further. Yi minus y average into xi minus x average upon xi minus x average whole square. If I cut this, I will get the same thing, right? So I can modify my equation as yi minus y average into xi minus x average upon xi minus x average whole square, right? This is the equation of your slope. This is the equation of my slope. You can see this. Yi minus y average into xi minus x average upon xi minus x average whole square. That is my m. Now, once I have m with me, I know that my line will always pass from the average. So I know my y average as well. I know my x average as well. I now know m as well. I can very well find the c also, right? So y average minus mx average is nothing but my c. Now let's take an example so that we'll understand what I'm talking about, okay? So we got these two equations. We'll keep it in mind and we'll try to solve one example here. As of now, we'll apply all the formula, right? So I know my x, I know my y. It's a machine learning, right? I am teaching for last many years. I have this data that if you are studying for 2 hours, you are getting this marks and so on and so forth. If you remember the example of car and all we discussed in the last class, I want to predict the car price based on various features, how we discussed. The same thing we are doing here as well. So I have this data with me. Ignore all these things for now, right? Only this information is what you have. X and Y. How many hours you are studying and how many marks you got. You are teaching your learners for last many years. So this information is handy with you. And now you want to create a machine learning model on top of your data set so that you can go ahead and you can do the prediction for the future students. And I know the formulas, right? Xi minus x average, yi minus y average upon xi minus x average whole square. I know this formula. And if I want to calculate this m, I need average also. Without average, I cannot do anything. So what I am doing is I am calculating the averages. Average of x, average of y. So this is my x average, this is my y average. These are my xi's, x1, x2, x3, y1, y2, y3. Right? xi, 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 x, yi, yi, yi. Now once I got the average, we know the formula. Xi minus x average, xi minus x average, xi minus x average. I got these numbers. Same way, yi minus y average, yi minus y average, and yi minus y average. What was the numerator of my formula? Xi minus x average into yi minus y average. That is the numerator. This multiplied by this is this. This multiplied by this is this. This multiplied by this is this. And I will be summing it up. If you see the formula back there, what was the formula? I am summing it up. Summation. So xi minus x average into yi minus y average. Whatever you are getting it, sum it up. So whatever I am getting here, I am summing it up. Whatever I got here, I summed it up. That is 19. What was my denominator? Xi minus x average whole square. Xi minus x average whole square. Sum it up. Right. What is the formula? summation of I is equal to 1 to n, yi minus y average, xi minus x average upon xi minus x average whole square. So I have to sum this up, which I did that. I want to sum this up, which I did that. Now divide it. 19 by 2, that is 9.5. So I got my 9.5 as m. I already know the average study hours, that is 3 hours. I already know the average marks, that is this marks. So 55.67 is equal to 9.5 into 3 plus C. Give me the value of C. My value of C is 27.17. Because this guys will go here. C will be this minus this. So I got my y is equal to mx plus c, where y is nothing but my marks, m is nothing but my slope, x is nothing but my study hours, and c is nothing but by intercept. I got this equation. Are you guys getting it? How this entire equation be calculated? Okay. All right. Intercept is nothing but when we are creating a line, x is equal to 0. This is my intercept, C. When your x is equal to 0, what is the value of y? Y is equal to mx plus c. X is 0. So this will become 0. So what is my y? Y is nothing but c. So when your x is equal to 0, your line is cutting your y-axis. So whenever it is cutting that y-axis, at what value your line is cutting? At what value of y your line is cutting? That is your y-intercept. Intercept is nothing but katna, right? It's intercepting. So it is cutting out there, and that is the output. Okay. Now, once all these things are done, now I want to find out whether this equation is making sense or not, right? Try to understand this. What machine does? This is my data set. Okay. Now, machine directly not create the straight line. Machine at the back end, what it try to do is it tries to basically reduce the error, right? I have to switch on my camera for explaining that. So let's see. Let me expand this a bit. Okay. So as of now, can I say, as per this data set which you can see, my line is this line, best fit line, which is passing from the majority of the points. But what machine will do? Machine will not give me this line in the initial step, right? It will try to create multiple lines. Machine will try to create multiple lines. Line can be like this, 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 line can be like this. So it will do multiple iterations, right? And whichever iteration will have the minimum error, that will be my best line. Is that making sense, all of you, till this point? Right? Machine will not, at the first go, machine will not create the best line. Machine will create the best line with multiple iterations. It will take this line, this line, this line, this line. Whichever line is best line, that means where the error is less. That is the best line. Okay. Now, let's say I have this line. This is the best line, which is passing from the majority of points. What can be the worst line? Can I say that? Okay, let me switch on the camera again. Can I say that when the line is the average line, this will give me the maximum error? Because see, when I start tilting the line, it will start passing from the points. It will start passing from the more number of points, all of you, right? When the average, at the average, you will have the highest error. But when I start tilting, you can see that your points will be touching the line, right? It will start touching the line. Majority of the points will start coming towards the line. But when you are having the average line, it is like the worst I can have, right? The worst line which I can have is the average line. Okay. So now let's come back. This is my worst line. This is my average line, which is the worst line. Average line. Okay. Why it is a worst line? Because see, for this point, I have a lot of error. For this line, I have a lot of error. For this point, I have a lot of error. For this point, I have a lot of error. For this point, I have a lot of error. Right? So, a lot of error. So, errors are more. So, the worst which I can have is average line. Okay. Till this point, are you guys clear, all of you? Why worst is average and why it is going to give me the maximum error? Right? Now, we'll come to one interesting thing. Okay. Let's take two scenarios. Scenario number 1 and scenario number 2. This is my first scenario where things are very nice. The data is very much linear in nature. Second scenario. Okay. This is my scenario number 1. This is my scenario number 2. In which scenario do you think that linear regression will work well? Scenario 1 or 2? 1. All are saying 1. Right? All are correct. Okay. So let's create a line which is the best line. Okay. And what is the worst line? The worst line is the average line. Okay. Now, can I say I will have more error with the average line? My error is more. Let's call that as SST. Sum of squared total. Right? What is SST? SST is nothing but the error coming from average line. Okay. So can I say that here SST will be the highest because average is the worst? Right? मेरा average line सबसे खराब line है. And if my average line is a bad line, the error which I am going to get will be higher. And when my error will be higher, can I say that my SST will be higher? All of you? Okay. All right. Now the error coming from the model. Model is this blue line, right? Model is this blue line. So SSE is the term. Sum of squared error. That is nothing but error coming from model line. In this particular data set, error coming from model line will be high or less? What do you think? Less? Yes? Perfect. So can I say that your SSE is lesser, or I can say way lesser than SST? Okay. So keep that in mind. Okay. Let's keep that in mind for some time. Let's come to scenario number 2. Can I say this is my average line? And this is my maximum error? That means that is my SST. Can I say my model line will also be something like this only, all of you? Because data is very much scattered in nature, right? SSE is nothing but the error coming from this blue line. This error, this error, this error, this error. SST is the error coming from the red line. So can I say that in this, error coming from the blue line is lesser than error coming from the red line? Error coming from the blue line is lesser than the error coming from the red line, right? That means SST is more than SSE. Here, can I say that error coming from the red line is almost same as error coming from the blue line? Yes. Perfect. Till this point, all of you guys clear? Jay and all. Now let me come up with one formula. 1 minus SSE upon SST. This is the formula. Now let's see the behavior of this formula. In this scenario number 1, can I say my SSE is lesser than SST? In my scenario number 1, SSE is lesser than SST, or I can say way lesser. So can I say that this guy will be very small? Because my numerator is very small, my denominator is very high. So small by high is what? Very small number, right? Smaller value divided by the bigger value is my smaller value. And 1 minus smaller will be what? More towards 1. More towards 1. Can I say that? अगर मैं 1 को माइनस करूंगा एक छोटे नंबर से, एक छोटे फ्रैक्शन से, सो मेरा वैल्यू कितना आएगा? मोर टुवर्ड्स 1 आएगा, राइट? यहां पर आते हैं. My SSE is almost same as SST. If these two are almost same, can I say this is nothing but 1 or almost towards 1? So 1 minus almost towards 1 is, I can say it's more towards 0. Yes. So can I say that in this particular type of scenario, this formula will give me the value more towards 1, and in this particular scenario, the value which I am going to get for this formula will be more towards 0. This value which we are talking about is known as R square. The another name for this is coefficient of determination. When your data is linear in nature and you are applying the linear regression, the SSC by SST, that is nothing but R square value, is coming out to be more towards +1. And when your data is scattered in nature, your R square value is coming out to be more towards 0. So whenever your R square value is coming out to be more towards 1, I can say that your model is giving me a good prediction. And when my R square value is coming out to be more towards 0, in that case, I can say that my model is doing a wrong predictions because error is more. Is that making sense, all of you? So here I have explained how to calculate this R square. Okay, let's see what happens here. What is SST? The formula was 1 minus SSE upon SST. SST is what? Average error square. Squared, sum of squared total, right? Error coming from average line. What is my average line? This is my average line. 55.67. Y is what? 55.67, the average line. Right? So now the error coming from 47 minus 55.67, 54 minus 55.67, and 66 minus 55.67, these are what? Error coming from the average line. And when I do the sum, it will always gonna be 0. Because you are plotting all the points on the average. And when you are plotting all the points on the average, it is gonna be 0. And I don't want 0. That is why I am doing the square. That is why it is known as sum of squared total. We are doing the square and we are summing it up. Right? So that is my sum of squared total. That is SST, error coming from the average line. Are you guys getting this, all of you? How SST is getting calculated? Now in the previous slide, we got the equation of a line as well. In the previous slide, we got the equation of a line as well. Y is equal to mx plus c. Now this equation is gonna give me what? This equation is gonna give me SSE. What I am doing? X ka value, I am putting the value of x as 2 years. I am getting the marks like this. I am putting the value of x as 3 years. I am getting this marks. I am putting the value of x as 4 years and I am getting this marks. So basically this is the marks coming from the model line. And then I am subtracting the original marks with the model line marks. These are the errors. Errors coming from the model. And I am doing the square of this also because I want to compare with this guy. So I am doing the square of this as well. And I got this number. So this number is your SST and this number is your SSE. SSE is coming from the equation of a line which we calculated. I am passing the various experiences out here and I am calculating the values. Whatever error is coming in is the error coming from the model. And here I am subtracting the average with the actual value and the error coming is the average line error. I am doing the square of this, as well. SSE is there, SST is there. 1 minus SSE upon SST is 1 minus 4.16 upon 184.16. I am getting the value of R square is 0.9775. As it is more towards 1, that means my model is good. Right? If it is more towards 0, in that case, my model is bad. Are you guys clear with this R square and its calculations? Coefficient of determination. Now, there is a problem with the R square. Now, what is the problem with the R square? The problem is, suppose let's say I want to predict my salary. Based on experience, based on my team size, based on my education, and based on my son's age or my kid's age. Let's say. Now, suppose I am creating a model only with the experience to predict the salary, right? So basically what I am doing is I am only using experience and coming up with the equation of a line. Salary is equal to M1 into experience plus C. Now this equation will have the R square value which we calculated, right? This will have some R square value. Let's assume the R square value is 0.8. Let's assume that. Now I am thinking, okay, let's introduce the team size as well. So salary is equal to M1 into experience plus M2 into salary plus C. In this scenario, my R square will increase further. Now I am thinking to add education as well. Salary is equal to M1 into experience plus M2 into your team, what is that? Team size plus M3 into education plus C. In this scenario as well, my R square will further increase. Let me add my son's age as well. Now, for my salary, my son's age is obviously not gonna make sense. It's not important feature for me. But still, when I am adding the another feature, which is my son's age, my R square will increase further. R square is having a tendency to increase always. Whether you are adding any important feature to predict the salary, or if you are adding any unimportant feature to predict the salary, your R square will always increase, right? That is the behavior of R square. And that is a problem. Because when R square will always increase, if you're adding any unimportant feature, then why are you increasing? But the behavior is like that. It will always increase. So what is the solution? Before I talk about the solution, why it is happening, let's talk about that. Here you can see, right? So we already discussed all these things. One is the perfect model, zero is the bad model, right? All those things we have discussed. Let me come to this part again. Let's read it from here. Understanding variations. Imagine you are trying to predict student test score based on how much they studied. Now you build a model that gives you a predicted score, but there is a question. How do we know if our model is actually doing a good job? To answer that, we look at the different types of variation in the data. Let's break it down. First one is SST. We discussed that. How far the actual scores are from the average score. Error coming from the average line, right? Think of it like this. If I did not build any model and just guessed everyone's score as the average score, how wrong would I be? SST measures total error if we don't use any prediction model at all. Because we are saying that average is what I am going with. So that is my SST. Second is my SSR, sum of squared regression, which we did not discuss. How much better is the model compared to using the average? This is SSE actually, typo. This is SSE. Because how much better your model is compared to the average, right? Model line. So that is my SSE. Lesser the SSE, our model is doing good job, right? Ignore this typo, which we discussed. SSE should be lesser, and lesser the SSE, good the model is. Okay. It measures the improvement of model gives us over the using just average. Next is your SSR. I just messed up, right? This is my SSE and this is my SSR. Okay. How far actual score from the predicted scores? I missed this slide. Give me a second. Just give me a second, okay? SST we are clear with, that is looking fine. SSR. What is the model with the actually? This is my SSR, which is fine. And this is my SSE. I'll explain this. Give me a sec. Sum of squared errors of an actual score from the predicted one. SSC lower. This one. Okay. Now this is the final one. All right. So let's talk about this again. Let me create a picture so that you will get a better understanding. This is my chart. This is my data set. Okay. And this is my average line. This is my model line. Okay. Now, we are discussing three terms. One is SST, which you are already aware of that. Actual value minus the average value, right? Actual value minus the average value. Average line will always give me the higher error, right? So actual minus average is what? SST. That we discussed. SSE also we discussed. What is that? Actual value minus the model value. Actual value minus the model value. Actual value minus the model value. SSE is less, which is good. Actual value minus the model value, prediction, right? And this should be less. This is normally high, right? Third one is SSR. What is SSR? Prediction value minus the average value. That is prediction value minus the average value. Prediction value, let me take this guy. Prediction value minus the average value. Prediction value minus the average value, right? Prediction value minus the average value. So try to understand. Actual value minus the average is your SST. Actual value minus the predicted is your SSE. And average minus prediction is your SSR. So your SST is normally high. SSE should be less. SSR should be high as well. Right? Why high? Because you can see prediction and average. It's high, right? Why it is high? Because your SSE is less. You are very close to the point. Prediction is good, but SSR is high. There can be a chance that SSE, SSR both are high. Or no? No chance, right? If SSE is higher, SSR will be lesser. For example, let's take this scatter data. I have this line, which is a model line, and I have this average line, right? My SSR will be what? Prediction minus your SST. It is lesser. Prediction minus average lesser, but prediction actual value is very far, right? So your SSR is also higher. Your SST is also higher. SSE also higher. Sorry, what I'm saying. SST is higher, SSE is higher, but your SSR is lower. SSR is what? Prediction and average. Prediction और average के बीच में तुम्हारा error कम है, तो SSR कम होगा. But SST और SSE क्या हो गया? ज्यादा हो गया. Right? So SST is nothing but your actual value minus the average value. SSE is nothing but actual value minus the predicted value, and SSR is nothing but average value minus the predicted value. If this guy is normally higher, obviously, if this guy is higher, that means your SSC and SST are same. And when your SSC and SST are same means what? This guy will be more towards 0. Because तुम्हारा actual value, sorry, average value और prediction value same है. Right? Your average value and prediction value is same. That's why your SSC is higher. That's why this two will be closer. Automatically SSR will become smaller. So when your model is the worst model is the worst model, in that case your SSR will be smaller. When your model is the best model, your SSR will be higher. Because the difference between the average and the prediction will be higher. And when that is possible? When your data is something like this. Average and the error is less. Nice linear relationship. Are you guys getting this, all of you? SST, SSC, and SSR. Still any doubts? Let me know. SST should be always higher because it's an average line. SSC can be higher or can be lower. If the data is linear in nature, SSC will be lower. If the data is not linear in nature, SSC will be higher. Now, when your SSC is lower, SST minus SSC will be lesser. Sorry, if SSC is lower, SST minus SSC will be higher, right? Because तुम्हारा मॉडल तो बहुत अच्छा काम कर रहा है, but average टाइम बहुत खराब है, तो दोनों का डिफरेंस बढ़ जाएगा. But when your SST and SSC both are same, so automatically your SSR will also become smaller, right? So that is the idea. So basically SSE should be lesser always, SSR should be higher always. Simple thumb rule, right? When SSC is higher, SSR will become lower. And I don't want SSC to be higher. Okay. So that is this terms which we have discussed. Now let me come to this part. This slide you already discussed, that R square is 1 minus SSC by SST, and you can see it's more closer. But wait, there's a trap. Adding more features, even useless ones, will always increase R square slightly. That's where we bring the adjusted R square value, right? So R square will always increase, whether the feature is important or not important, R square will always increase. And that is the problem. So how will I take care of that? How will I take care of that? I'll discuss in some time, but why it is happening like this? Now here you have to imagine, let's assume that we are in the higher dimension space. Abhi, as a human, we can only understand 3-dimension space, right? But suppose we are in the higher dimension space. When my dimensions are increasing, automatically my data will become linear, right? जब भी मैं higher dimension space में जाऊंगा, just think of a room, right? In a room, lot of balls are there. Now, if I try to look at the ball from some angle, right? There can be a chance that at one angle, the balls will be coming in linear in nature. So just think of a scenario when we are having higher dimension space. So when we are increasing the dimensions, automatically my linearity will increases. And because of that, my R square is increased. Because when my linearity will increase, my error will be less. Error will be less, R square will be more. So that is the one of the reasons. So more features, more flexibility. Each feature, independent variables, gives the model more wiggle room to fit better with the data, even if the feature is irrelevant. More features, more chances to reduce the SSC. Lower the SSC, higher the R square. Even if the new feature does not make logical sense, the math still tries to optimize the fit of the line, plane or hyperplane. In the 2-dimension space, we are creating a line. In the 3-dimension space, we are creating a plane. ऐसा समझो. When we are at the 2-dimension space, I am creating what? I am creating a line. When I am at the 3-dimension space, I am creating one plane. And when we are at the multi-dimension space, we are creating hyperplane. So basically, when my data is having more dimensions, automatically my data will start becoming linear in nature. And because of that, my SSC will reduce. Because अगर मुझे linearity मिल जाएगा, तो फिर R square तो कम हो, R square तो बढ़ता जाएगा, right? So that is how it is. So that is one of the reasons. Second reason is what? Regression is optimized to minimize SSC. What is the main purpose of regression? The main purpose of regression, I told you. जब मैंने कैमरा ऑन किया था मैंने बोला था कि मेरे पास एक लाइन ऐसी बनानी है. मशीन क्या करता है? मशीन विल स्टार्ट क्रिएटिंग मल्टीपल लाइंस एंड वंस इट विल गिव मी द बेस्ट smaller SSE, that is my final model. So what is the main purpose of regression? The main purpose of regression is that come up with a line or come up with a plane or come up with a hyperplane which will reduce your SSE. And if it will reduce your SSE, what will happen? Your R square will increase. So when you are adding one new feature, my machine will try to reduce the SSE. And while doing that, my R square increases. Right? So that is the second reason rather. So regression is optimized to minimize SSC. Linear regression always tries to minimize the SSC, sum of squared errors. When you add another variable, the algorithm will tweak the coefficients to reduce SSC further. This automatically causes R square to increase because you are dividing by a smaller new SSC. Even if the new features does not actually help, the model will force a tiny improvement in SSC due to overfitting. Right? Overfitting and all, don't worry about that. We'll discuss that in the machine learning sessions. Third is R square never penalizes useful features. Sorry, useless features, right? For example, we took the example, I want to predict the salary based on my son's age. Now that is a useless feature, right? My son's age does not matter or does not decide my salary. So if you are adding that in the model, what happens is that it is not penalizing that. If I am adding any irrelevant feature, it should penalize. So in regression, that does not happen. R square never penalizes for useless features. R square only looks at how much better your model predicts the outcome versus the mean. मुझे ऐसा लाइन लेके आना है जो कि एवरेज से अच्छा हो, उसका वही काम है, right? So what machine learning will do, what regression model will do, it will try to come up with a line which will reduce the SSC and increase the SSR, right? It does not care how many features you used to get there. मेरा काम क्या है? अच्छा आर स्क्वायर लेके आओ, चाहे तुम कितने भी फीचर डाल दो, चाहे वो फीचर काम का हो, चाहे वो फीचर काम का ना हो, आई डोंट केयर, राइट? दैट इज द end goal of the regression, and because of that this problem is happening. So it will happily go up even if you are cheating by throwing 10 useless columns just to get a tiny SSC decreases, right? So that is one of the problems which we have. This overfitting slide we'll discuss later on because I don't want to overwhelm this. So now what is the solution? We got, okay, these are the problems and these are the reasons why it is happening. When we are going to the higher dimension space, my R score increases. It is not penalizing the useless features, right? And at the end, the third reason was regression is optimized to reduce the SSC. तो ये तीन रीजन की वजह से मेरा R square बढ़ता जाता है. तो उसको टेक केयर कैसे करें? How will I take care of that? I will be creating the new measure called adjusted R square value. The formula for the adjusted R square value is this, right? Now what it does, it penalizes, right? It penalizes, it punishes, right? How? Let's try to understand this. Suppose I am predicting my salary based on the experience, based on the team size, based on the education, and based on the son's age. How many features are we using to predict the salary, all of you? How many features are we using to predict the salary? 4. Upon adding multiple features, won't that make the model follow multicollinear? That is what we have to check, right? We have to check from the chart. If the features are multicollinear, we have to remove that. It is not always the case that if you are adding more features, multicollinearity will happen. It's not compulsory, right? For example, I'll give you one example. Suppose I want to predict the house price, okay, based on the area of my house. When my area is increasing, my house price is increasing. Same way, I want to predict my house price based on the distance from the city. When my distance is increasing, my house price is decreasing. Is there any relation between area and distance? No. So will it cause multicollinearity if I take both the variables? No. So it's not always the case. That's why you have to check it out, whether multicollinearity is there or not. For that, we have those charts, correlation charts, and which we have seen. Okay. All right. So let's come back. So 4 features are there, right? So we are using 4 features. What adjusted R square value does, it says that whatever features you are taking in the model, चाहे वो फीचर अच्छा है, चाहे वो फीचर खराब है, I will penalize always. Whether the feature is important or the feature is not important, I will always penalize you, right? चाहे तुम अच्छा फीचर लेके आओ, चाहे तुम खराब फीचर लेके आओ, मैं penalize हमेशा करूंगा. I will always penalize you. Now let's see how it is penalizing. Total features are 4. In this formula, this k is nothing but my number of features. How many features we have? 4. N is nothing but my total number of training data, right? On how many data records we are training the model. That is N. Now see this formula. Suppose you are taking k is equal to 4. My k will become what? 4. Or can I say that when k is increases, my denominator will decrease? All of you? Can I say that? When my k will increase, my entire denominator will decrease because you are subtracting n with that. k बढ़ेगा तो ये वैल्यू बढ़ेगा एंड ये वैल्यू बढ़ेगा तो मेरा ये पूरा घट जाएगा. यस, ऑल ऑफ यू. Now, if this is reducing, can I say that this entire fraction will increase? Because my denominator is less. Automatically, if I'm dividing with a smaller number, this guy will increase. And if this guy will increase, can I say that I am multiplying this entire term with an increased fraction or a bigger fraction? All of you. Automatically, this will also increase. Automatically, this will also increase. And if this will increase, can I say that I am subtracting 1 with a increased fraction and that will decrease the value? Right? 1 minus a bigger fraction will reduce the value. That means your R square adjusted is reducing. So can I say that because of this k, my adjusted R square value is decreasing? That means this k is nothing but my penalizing factor. It is penalizing the R square value, right? So when your k is increasing, that means you are adding a feature, whether it is relevant or whether it is irrelevant. I will penalize you, right? तुम अच्छा लेके आओ, बुरा लेके आओ, मैं तुम्हारा penalize करूंगा. As simple as that. Okay? That is your adjusted R square value. Now let's see out here as well how it is getting calculated. So in this particular data set, we have 3 values. So my N is 3. In 3 records, I trained my model. So N is 3. How many features did I use for training the model? Only 1 feature. So my K is 1. So 3, that is N. 3 minus 1 plus 1 is 1. And this is 3 minus 1 is 2. So 2 by 1. Right? 2 by 1 multiply by this thing. 1 minus this thing. I am getting this thing. My R square value was 0.9775. My adjusted R square value is bit lesser. You can see it's bit lesser. Why it is lesser? Because of this penalizing factor. So my adjusted R square value will always be lesser than your R square value. Okay. Is that making sense, all of you? All right. Now what I will be doing is I will be showing you this equation, right? What was the equation? The equation was this 9.5 into study hours plus this. Let me write one code in Python. You will not understand Python because we did not discuss Python till now. But I wanted to show you that whatever we discussed, itna sara maths humne padha, right? We discussed a lot of things. But in Python, I just have to write 3-4 lines and I will get this same equation. Exactly the same equation will I get. I will get, right? Let's see. I'll copy this data set. Let's save this in Excel. Okay. And let me open Python. So here you can see Python page coming in. Let me copy this data. Control C. Don't worry about all these codes. We are going to learn all these things in detail, right? So don't worry about that as of now. This is my data set, study marks and hours and marks. Ready to see the magic? What are the values? 9.5 and 27.17. 9.5 and 27.17. Exactly the same numbers coming in, right? So whatever we have discussed out here, all these mathematics, Python is doing in 3 lines of code. In fact, this is the main code, this line, only 1 line, right? So that is the power of Python. And why we are doing this? Suppose tomorrow a new guy comes in and he's saying that I am studying for 1.5 hours. How much marks will he get? 9.5 into 1.5 plus 27.17. These many marks he will get. My model will predict this. Regressor dot predict. How many marks? 1.5 hours. I have to convert that to an array. Give me a second. Let's make it 1 and let's copy this. Let me do one. Let me copy this. So let's say this is my new student, right? This is my new student, and he is saying that I am studying for 1 hour. So how many marks he will get? I will just passing my new student out here, and you can see that he is going to get 36 point something, right? Here, I think the calculation was wrong. 9.5 into 1. I gave 1.5. Sorry, I gave 1.5, right? So if let's say this guy is 1.5 marks, let me do this again. 1.5 hours. Control C. Clipboard. Drop it. Right. So 1.5, you can see. I'll get the prediction value 41.4. 95.1.5 plus 27.17. See this? Exactly the same. So now my model is ready. Model will help me to predict in the future, right? So I trained on my past learners. Now you come up with a new learner with how many hours he or she is studying. I can very well tell how many marks he or she will get. So my model is ready for doing the predictions. Although you will not understand this as of now, what code I have written, that's okay, that's fine. But logically, are you understanding or not is what important. Are you guys clear with this, what we have studied and discussed? Okay. All right, so this is what I wanted to cover, I guess. Pretty much okay. We discussed about this. In the next session, we are going to talk about probabilities. Okay. That will be the another topic which we should be aware of as a data analyst and data scientist. Any doubts you guys have? Let me know. I'll share this PPT. Yeah, I'll share this PPT. Give me. I'll just share it. Give me a second. Any doubts, any queries, any concerns, anything which you are not clear with, you can let me know. Recorded class, I think you are already getting it. Are you not getting the recordings of the previous sessions? Okay. All right. So